In this video, I'll be discussing all the important topics of fourth module. If you have watched my previous video, I have uploaded all the module-wise important questions. So as an extension to that, I'll be discussing answers of fourth module here. So first topic we have is functional dependencies and interference rules. So functional dependency is a constraint between two sets of attributes from a given database. So let's consider a relation R. A set of attributes X in relation is said to be functionally determine another attribute Y, which is also in the same relation, if and only if each value of X is associated with at most one value of Y. So which means that if X is the determinant and Y is the dependent, at most one value of Y should be associated with X, the determinant. X determines Y. So this is what functional dependency basically means. So it is a property of semantics and meaning of attributes. So by using functional dependencies, we can get to know the meaning of that particular attributes. So this would be helpful in the normalization topic, which we would be discussing in the further. So discussing about inference rules, there are 6 inference rules majorly. So we need to write the inference rules in same order. So IR1, inference rule 1 states that it is reflexive rule, which states if X is a subset of Y or X covers Y, then we can say that X also determines Y. Then we have argumentation rule, which says if X determines Y, and let's take an attribute Z such that XZ should determine YZ. So group of attributes, here let's take A determines B. So group of attributes in A are XZ should determine group of attributes on B, YZ. So Y and Z are associated with A, or are associated with X and Z. So that's what it means. Then we have a transition rule. If X determines Y and Y determines Z, then we can write X determines Z directly. Then we have decomposition rule. X determines YZ. That means X can determine Y and X can determine Z also. Then we have union. If we union X determine Y and X determine Z, in order to union, you need to have a unique, you need to have a common attribute here. Here the common attribute is X. So you can combine them in such a way that X determines Y, Z. Then the 6th rule we have here is pseudo-transitivity, which says if X determines Y and YZ determines Y, WY determines Z, then we can write W and X determines Z. So this is about pseudo-transitivity. These inference rules would be used in order to calculate the closure, find the prime attributes, and in the further questions we'll discuss. Here we have the problems based on functional dependencies, closure, and identifying the candidate key prime attributes and non-prime attributes. So starting from the first question, we have a relation A, B, C, and the functional dependencies are given as follows. So A determines B, B determines C, and C determines Z. So our first step would be to find closure of all attributes. So here attributes we have A, B, C, right? So let's start finding closure. Closure is depicted as A with plus notation on the top. So firstly, any closure of any attribute would have itself, it will consider itself first. So we'll write A here. Followed by that, we need to check if A determines any other attribute. So here A determines B, right? So we can include B also. Next, check if B determines any attribute. B determines C. Check if C determines any attribute. C determines D. So A closure is A, B, C, and D. Now moving on to B closure. So first we need to write B, and then B determines anything. Check in the functional dependencies we have B determines C. So I'll write C. Next, after we have C here. So now check if C determines anything. C determines D. So I'll write D also. So after that, D determines anything. No, it's not there in the functional dependencies. Next, we'll write C closure. C closure determines C firstly, and then C determines D. So I'll write D here. Then D closure, I'll write D closure determines D first, and then check if D determines any other attribute. No, there's no functional dependency for D here. So yeah, these are the closures of all the attributes. Our first step is done. Our second step is to check which attribute or which closure determines all the attributes, comprises of all the attributes. So here, if you check here, D is also there because D is included here, right? A, B, C, D. So if you check at A plus A closure, we can state that A closure as A closure determines all attributes. We can say that it is the candidate key. A closure, no, we'll write A here. Candidate key is A. So understanding the definition of candidate key, so it could be one attribute or a set of attributes within a relation that uniquely identify each tuple or the row here. So A closure uniquely identifies A, B, C, D, right? So A determines B, B determines C, and C determines D. So candidate key here is A. So next we have prime attributes. So all those keys which help to uniquely identify the other attributes, like candidate key here, right? So all those which come under candidate key are considered as prime attributes. So we have A here, and non-prime attributes are those which do not fall under the excepting the prime attributes, whichever is left out, write it as non-prime attributes. So B, C, and D. So this was about our first problem. Looking at the second problem, relation has A, B, C, D, 4 attributes, and functional dependencies are given here. We need to find the closure, prime attribute, and non-prime attribute. So our first step is to find closure of all attributes. So let's start from A closure. A closure here, I'll write A and check if A determines anything. A determines B. Now I'll check if B determines anything. B determines C. C determines anything. D. D determines A. So now because I have written A here, I can't write it again. So it's the same. So A, B, C, D is the closure for A. Next, writing closure for B. Firstly, I'll write B and check if B determines anything. B determines C. So I'll write C here. C determines D and D determines A. Right. So I should write A also. C closure. I'll write C first and check if C determines anything. C determines D. D determines A. A determines B. And B determines C. So I need not write C again. Next, I'll find D closure. D determines, first D I'll write and check D determines anything. D determines A. A determines B. B determines C. And C determines D. So I need not write D again. So I have found closure of all the attributes. Now I'll check which attribute determines all other attributes. So A attribute determines all other attributes. B also determines the same. C also determines the same. And D also determines all the attributes present in the relation. So I can say candidate key here are A, B, C, and D. So prime attributes are the same. Write it as it is. And non-prime attributes are those attributes excluding the prime attributes. So excluding A, B, C, D, do you have anything in the relation? No. So it's null. So this was about second question. Third question, are the relation as A, B, C, D, E, F, I, J, and then the functional dependencies here are A, B determines C, A determines D, E, B determines F, F determines G, H, and D determines I, J. So here in the previous questions, what we did, we found closure of all the attributes, right? Because it was easy. Here there were only 4 attributes and it was easy to find closure. But then now here we have A to J, it will become lengthy. So the one more step or a shortcut for that is we'll look into the RHS part. So firstly we'll look into RHS part of functional dependency. Write down as it is what is being determined. So on the RHS part, what do we have? C, followed by that we have D and E, then we have F here, and then we have GH here, and then here I have I and J. So in order to obtain a candidate key, it has to cover all the attributes, right? It has to determine all the attributes. So if you check, I have C, D, E, F, G, H, I. So what are missing? A is missing, B is missing, right? So I'll write whatever is missing here initially. Okay. Now I'll take closure of A, B and check if it determines all these. So if I take A, B closure, firstly I need to write A, B, and then I'll check what if A determines anything, B determines anything, and combination of A and B determines anything. So first A determines D and E. Next I have B. B determines anything, B determines F. So A done, B done. Now I'll check the combination AB. AB determines C. C I have written. Now these two are done. Now let's move to D. D determines anything, D determines I and J. Okay. And then E determines anything? No. Combination of DE? No. F determines anything? F determines GH. So I'll write GH here. C determines anything? No. I determines anything? No. J also no. G? No. H? No. So I have written all the possible closures for AB. All the possible closures for AB. So I can say that as AB closure gives or determines all attributes, it can be considered as candidate key. So whatever is remaining, so prime attributes would also be the same A, B, and whatever is remaining non-prime attributes would be those. So AB is done, so C, D, E, F, G, H, I and J would be the non-prime attributes. So this was about the third question. Now let's look into the fourth question. The relations are given here, A, B, C, D, E, and then the functional dependencies are also specified here. So let's use the shortcut method. So shortcut is look into the RHS part and write down whatever is being determined. So here we have B, D, C and A. So A, B, C, D is covered, E is missing. So I'll write E here and then I'll try taking E closure and check if E closure determines all these. So like how we did in previous question, let's check. E closure determines E first, then C first. Then check if EC combination is there, no. Check if C determines anything, no. So E closure is not possible. Now let's start with A, B, C, D, E. Now let's club E closure with A, B, C and D and check. Now I'll write AE closure. So for AE closure, first I'll write A and E as it is. Then I'll check for A. For A determines anything, A determines B. And then E determines anything, E determines C. And then AE determines anything, no. Check if B determines anything, no. C determines anything, no. Combination of BC determines D. So I have got A, B, C, D, E, all the attributes in the relation. So this is one candidate key, AE closure. Now I'll replace it with B and E closure. I'll check for BE closure. So first I'll write BE as it is, and then B determines anything, no. E determines C, right? Now I can take combination of B and C. So BC determines D. I can write that. Now C determines anything, no. D determines anything, A. D determines A. So I've got A, B, C, D and E, all the attributes in the relation. So I can consider this also as a candidate key. Next I'll take CE closure. Okay, I'll take CE closure and check. So I should write C and E as it is. E determines C and C combination is there, no. So this can't be considered as, you can't write anything further, right? So you can't consider this. Now I'll take DE closure. So for DE closure, let's write D and E as it is. Next E determines C, D determines A and A determines B. So this is also candidate key. So I can write that candidate key is equal to AE, BE and C and E. So the prime attributes here would be A, B, C and E. The ones which are not a part of prime attributes are considered as non-prime attributes. So that is only C. Now let's look into the last question, that is the relations are given A, B, C, D, E and the functional dependencies are specified here. So you can solve this either by the first method or the shortcut which I've told. So you have five attributes here. So instead of writing, you'll write A, B, C, D, E. Along with that, you need to consider AB pair and then BC pair and write it further. So instead of that, we can look into the shortcut. So that is look into RHS, write down whatever is being derived. So AB derives C and then BC derives D, D derives E and F derives B. So what is missing here? A is missing here and F is missing here. So let me write AF here. And next I'll try finding closure for AF. So A closure is first, A I'll write, F I'll write, and then A derives anything, I'll check, no. F derives anything, F derives B. So when AB, if I take combination of AB, it derives C, right? Next, if I take combination of B and C, it derives D. Next, if I take D closure, D derives E. So I've got A, B, C, D, E and F also. So I'm done with AF. AF is one candidate key. Now I'll check for BF. So let's see BF determines all the attributes or not. So BF, I'll write first B and F as it is. And then I'll check if B determines anything, B determines anything, no, B does not determine anything. F determines anything, F determines B itself. So this can't be considered. Next I have CF, I'll take CF. So CF, if I write, C determines anything, no. F determines anything, B. So I can't consider this also. Next I'll take DF closure. I'll write D and F. D determines anything E, F determines anything B. Try taking combination of any of these and check if any of them would determine anything in the functional dependencies. No. So I can say that finally only the candidate key which I have obtained is AF. So I have checked for all others also. So I'm not able to find the combinational candidate keys except AF. So AF are the candidate keys. So prime attributes here would be A and F, and non-prime attributes would be except these. I have B, C, D and E. So I'm done with solving questions on finding closure and finding closure, prime attributes, non-prime attributes and candidate keys. So these questions were taken from previous year paper. So I hope this concept is clear. Moving on to the next topic, we have to write. So there'll be a question on finding this closure and this problem. Along with that, they can ask the algorithm for closure also. So understanding the algorithm in pretty simpler terms. So we are determining x plus. X plus is closure. So closure of x under f. So input is a set of functional dependencies on relational schema R. So R was given here and then functional dependencies were specified here. So firstly, any closure of x would be x itself. That's what we did, right? First, E closure means first we wrote E and then we checked if E derives anything else further or not. So this needs to be repeated until and unless we obtained x itself. So you started with this and you started finding if it derives anything and you kept on going until you reach this point. You need to keep on repeating this. Next, here we have for each functional dependency y, determining z in f do. So if x covers or x is a subset of y, then I can write x closure is equal to x closure union z, because z can also be included. So here let's take an example. A determines B, B determines C, and C determines, okay, A determines B, B determines C. So I can write, if I write A closure, I'll write A first, and then B is being determined by A, right? So I'll write B also. And here the condition says that there's a new variable, there's a new attribute C, such that I can write A closure union C, because C is being derived or determined by B and B is being determined by A. So I can write A, B and C for A closure. That's what is explained here. Until you keep on repeating this until you encounter the A itself at the end. So that was a pretty simple explanation of determining the closure algorithm. So you can write it in your own words. Next, moving on to the minimal cover. So before moving on to the minimal cover algorithm, let's solve the problems first. So once you solve the problems, you'll get to know how to you'll get to know the steps, and it'll be easy to understand the algorithm. So here they have asked to find the minimal cover for the following functional dependency. Here the functional dependency is given. My first step would be to look into the RHS part, and decomposition rule needs to be applied here, that is split. So I'll look into the functional dependency first. I have A determines C. So RHS you can't split it, right? C you can't split it further. D also you can't split it further, but then A, D, F can be split further, decomposed further, such that E determines A, E determines D and E determines F. We have seen that in the inference rules here, right? So here initially I need to remove A determines C. Assume that we have removed A determines C. Now write A closure. If you write A closure, you'll get A first and then check if A derives anything except this. If you check there is no other combination or no other possibility of functional dependency which would derive C, right? So we can say that this particular functional dependency is not redundant, so we need to keep it. Our aim in the second step is to remove the redundant dependencies. Simple. If you try understanding this, you might get confused. But then in simpler terms, I'm saying that you should find closure of all these by assuming that you have removed. If you obtain the RHS part, then it is redundant, remove it off. If not, keep it. So for AC plus AC closure, if I write, I can get A, C, and then close this. AC determines D, close it. A closure, you have anything here? No. A closure is C. A determines C. C is already written, so you can't consider it. C closure, anything? No. So you have obtained only A and C. So AC determines D is a unique one. It is not redundant. Not redundant. So keep it. Now let's look into E determines A. So assume that you have removed E determines A. Now write E closure. So if you write E closure, you'll get E and then D and then F. Now D closure, if you see, no. F closure, there's nothing. F determines nothing. D determines nothing. E and any of these combinations, no. So you can state that E determines A is unique. It is not redundant. So keep it as it is. Next, E determines A is done. This is keep it, keep it, keep it. Now E determines A, or D, sorry. E closure. Close this. Find E closure. We have E and then E determines A. E determines F. Check A determines anything. A determines C and D. And if F determines anything, no. Any of these combinations you have, AC determines D. D I have written already. So here E determines D was the functional dependency which I took and which I assumed to be, which I initially removed it and checked if E closure I would get D or not. And when I checked, I got D here. That means this is not unique one. There are other ways of deriving D. That means this is redundant. So remove it. Remove this. Now I have E determines F. Finding E closure. I have E. Close this. Check. E determines anything. A and D. Let's write A and D. There's no attribute which would determine F, which I wanted on the RHS part. So it is not redundant. Keep it. So I'm done with all the functional dependencies, right? So I'll write the updated list now. So it would be A determines C, AC determines D, E determines A, E determines F. So next, I'm done with the second step of removing the redundant dependencies. Now my third step is to look into the LHS part, remove redundant dependencies. The basic idea of minimal cover is that you're eliminating all the redundant ones, redundant dependencies. Okay. So looking at the LHS part, I have AC. So firstly, I'll decompose it and then remove the redundant dependencies. So AC could be written as, it can be written as A determines D, C determines D. Right. So again, I'll find A closure and C closure. I assume I'll close this and check now. A determines C, A firstly, and then C, and then AC determines D, and D determines anything, C determines anything, no. So here A determines D, and when I found A closure, assuming that I've removed this, I got D itself, which means that this is redundant. So I need to remove this. C closure, close this. C closure first, write C. C determines anything? No. So this is unique one. So keep it. So again, I'll write the updated functional dependency. So I have A determines C, and out of AC determines D, I need to keep only C determines D, and then E determines A, and then E determines F. Now this is the functional dependency, final minimal cover, or you can club the common ones, as we have two E's here, right? So you can club that, and A determines C, C determines D, so A determines D. A determines C, D, sorry, and E determines A and F. So this was about finding minimal cover. So looking at the next example, we have, consider a relation R which has attributes A, C, D, E, and H, stating satisfy the following functional dependency. The functional dependency is given here. So find the canonical cover for this set of functional dependency. My first step is to look into RHS part, decompose it if necessary. So RHS part, I have AD here. So I'll decompose it and write A determines C as it is, AC determines D, E determines A, and E determines D, E determines H. Okay. Next step is removing the redundant dependencies. So firstly, I'll consider A determines C. and write A closure. Close this and write A closure, you get A. A determines anything further? No. So this is unique. I have not obtained C here. So this is unique one, or it is not redundant. So I'll keep this. Next I have AC determines D. So I'll write AC closure. So I'll write A and C first. A determines C. C is there already. And no, that's it. C determines anything? No. A determines anything? No. So this is also again unique because I have not obtained the D here. So it is unique or not redundant. Thus keep it. Next, coming to E determines A. Unique, unique, unique. I'll check this. E closure, I write E, A. A determines C. E closure is A. And A determines C. So A determines C. For E determines A, I have E closure. Close this and check E closure. I have E determines E firstly, and then E determines D I have, and E determines H I have. I have not obtained E determines A, right? So this is unique or not redundant. Keep it as it is. This is also fine. Next, check for E determines D. So E closure again. Close this. Write E determines anything A and H. E, A and H. Now check if E determines anything further. I've written A determines anything? C. A determines C, right? And check if H determines anything? No. H doesn't determine anything. Now check if any of these combinations determine anything. So AC is there here. AC combination I get D here, and D E determines D here. So that means it is not. This particular functional dependency is not redundant because without this also I can obtain D. So I need to remove it. Next I have E determines H. So E closure, assuming that I have removed this, I get EAD, and A determines C, AC determines D. So I'll write EAD, C, A, D, C and D, same. So I have not obtained H here. So this is unique or not redundant. Keep it. So I have removed only E determines D. So this is the redundant one. So I'll write functional dependency updated one, that is A determines C, AC determines D, E determines A, and E determines F. So E determines H, sorry. So this is similar to the previous question. I had found this question in the previous year paper, so I wrote it. So third step, look into LHS part, decompose it, and then remove the redundant ones. So here I have AC determines D. So I can write, for this I can split it as A determines D and C determines D. Now A closure I'll write, C closure I'll write. A closure without this would be A determines C and AC determines D. So without this also I have obtained D. So this is redundant. I need to remove this. This is not, if this is redundant, this won't be redundant, right? So I'll keep this. So finally I can write FDS, A determines C, C determines D, E determines A, E determines H. So this is the final answer. So now that we have understood how to solve the questions for minimal cover or canonical cover, we'll look into the algorithm. So understanding the algorithm. So finding minimal cover F for a set F for a set of functional dependencies E. So E is the functional dependency here. Input is a set of functional dependencies E. First set F is equal to E. First take minimal cover as E itself, the same functional dependency, the entire thing. Okay. Next we'll replace each functional dependency X in which X determines A1, A2, A3 and so on in F by N functional dependencies such that X determines A1, X determines A2 and so on. So I'll check if without X determines A, if I determine A itself, that's what we did here, right? Without this I'm checking if E determines D is obtained here, and if it is obtained here, it is not redundant, remove it. So removal of extra attributes B from the temporary functional dependency which I've taken, the set which I've taken. Next I'll check in F also, same. by removing that if I'm getting the equivalent one or not. If I obtain the equivalent one, then fine. If not, if I obtain the equivalent one, then remove it. If not, then keep it because it is unique one. Remove of redundant dependency, x determines A from F star. So this was about minimal cover algorithm. You can write this in simpler terms also. So we are done with closure, minimal cover. Now we'll move on to equivalence of functional dependency. Equivalence topic is pretty easy. Here again they can ask the algorithm and give us a numerical or a problem on equivalence. So the algorithm says that two functional dependencies are taken, x and y. Okay, two functional dependencies are given, x and y. We need to check if x covers y. If x covers y, then we need to consider functional dependency of y and find closure using x functional dependencies. If it determines, then x covers y. Opposite to that, y covers x. Consider each functional dependency of x and find closure using y functional dependencies. If it determines, then y covers x. If these two are true, then x and y are said to be equivalent. So let's look into the problem. You'll understand it better. So firstly, I'll consider x covers y. So if x covers y is given, then first I'll write consider y is equal to A determines B, B determines C, and A determines C. So now I'll take, I have A determines B and B determines C, right? So A and B are there in X. So I'll write closure here by considering this. Okay, so A closure here I'll get A determines B, B determines C, and C determines, no, C doesn't determine anything. So A, B, C. And on the RHS of X I have B and C. B and C is obtained here. So X covers Y is true. Looking into B closure, I have B closure is B firstly and then C, right? B closure is B and C. Here B determines C, B determines C. So this is again X covers Y. These two are true. Now I'll check for Y covers X. So for this I'll consider X. So I'll write X. A determines B and then B determines C. I'll take A closure. Here also A and B is there, right? So I'll take A closure now. A closure is A, B, and B determines C. So this is accepted. A determines B was required and I've got A determines B, right? So this is fine. Next I have B closure. So for that B would be there first and B determines C is there. So this is also accepted. Here I can write Y determines X. So now that X determines Y, X covers Y and Y covers X, I can write X and Y are equivalent. Looking into the next question here we have. So given below are two sets of functional dependencies for the relation R. So these are the attributes. We need to check if they are equivalent. So I'll take this as X and I'll take this as Y. These functional dependencies as Y. So first condition I should take X covers Y and check if this is true or not. So for this, find Y using X. So I'll write Y. For Y I have A determines BC and D determines AE. Now I have A, AB, D and D here, right? So I'll write find Y. I need to find A and D closures using X. So A closure and D closure. I want these from X. So I'll check if for A closure, if I get BC from X, I'll consider. I'll see. So A closure is A I have written, and from X if I consider A determines B and AB combination determines C. So B and C. I wanted BC, I have got BC, fine. Next D closure. I should get AE. So I'll write D closure is D first and D determines AC and A determines B and D determines C. Here I have D, right? So D determines E. So here I wanted AE and here I have obtained A and E along with other attributes. So fine, this is also true. So I can say this is true. X covers Y. Next I'll take Y covers X. That is find X using Y. So I'll write X. A determines B, AB determines C, D determines AC and D determines E. Now I'll check. Here I have A and D, right? So A, AB closure, D and D. So I'll write A closure first. I'll get A I want B here. So A closure is A derives BC. I wanted B, I've obtained B, so this is correct. Next I'll take AB closure, AB. I should get C. Now let's check if I get C. A derives BC, AB I'll write. Next A determines BC, B is there, C I'll write. Next I'll check D determines AE. So here I wanted C, here C is there, so this is also fine. So I can say that Y, okay, this is done, this is done. Now I'll check for D. D closure if I write, I should get ACE. Let's check if I get ACE from Y. So D closure is D first. For D I get AE and A determines B and C. I wanted ACE, I've got AEC. So considering this entire thing I can say Y covers X. So considering these two I'll say that X and Y are equivalent. So here we are done with the equivalence topic, informal guidelines, which is a very important question. So in this only I have explained the anomalies, different types of anomalies. So the first guideline says that semantics in relational attributes must be clear. That is, the guideline states that whenever we group attributes to form a relation, each attribute should represent some relationship instance or should have a proper meaning. So attributes of different schema must not be mixed in the same relation, and entity and relation must be kept separate. Understanding this first guideline with an example, here I have, looking at the example, I have employee. So in employee entity, I have ename, SSN, bdate, address and dnumber as the attributes, which is fine. All these are related to employee and they have some sort of meaning, right? Next, coming to employee details, I have ename, SSN, bdate, address, dnumber. So far it was fine, but then D project number, the department project number is not necessary here. So it is not property of employee details. So this is a wrong design. That's what the first guideline says. So we need to avoid such situations. So this was about first guideline. Moving on to the second guideline, redundant info in tuples must be reduced. So info stored redundantly leads to wastage of storage, leads to update anomalies. What are update anomalies? Those situations which need to be avoided while designing a database. That is, we have three types of anomalies here: insert anomaly, modify and delete. So guideline 2 states that design a schema that does not suffer insert, modify, delete anomalies. If there are any, then note them so that applications can be made to take them in account. So firstly, we'll understand what insert, modification and deletion anomalies are. So insertion anomaly states that to enter details of employee here, so details of his department also must be entered. So if you want to enter an employee name, you should also enter the department details. But it is difficult to enter details of department with no employee in it. So if you want to enter the department details, but then you don't know the employee name, it will become difficult, right? So it results in null values at that time. For employee, it will be null. For department, there will be some value. So that will lead to insertion anomaly. In modification anomaly, if one value of attribute, suppose manager SSN of department is changed, then that value should be updated for all employee tuples in same department. So if this is changed, then the employees who work under this particular manager, in those rows also, the values need to be changed or modified. That's what modification anomaly states. Then we have deletion. If you delete the last employee of department, then the details of that employee also no longer exist in that database. It's fine. So far it's fine. But then in those details, we have department number, department name also. So in other tables, those values will get deleted. So that again leads to a problem, right? So that's what deletion anomaly states. So while designing a schema, we need to make sure that all these three are avoided. So yeah, this is the table. This table is a result of join of employee and department. So joins of base relations lead to update anomalies. Yeah, so this was about second guideline. We have third guideline here, which says that we need to reduce null values in the tuples. So null values can depict that at present the value is unknown, but may be known in future, or maybe not, may not be applicable to the tuple at moment, or the value is known to exist but unavailable. So null value leads to problems like confusion in count and sum operation. So the guideline states that relations should be designed in such that their tuples will have fewer null values as far as possible. So attributes with null frequently could be placed in separate relations with primary key again to link that. Next, the last anomaly we have here is generation of spurious tuples. Spurious tuples are unwanted tuples which are generated, right? So they should be avoided at any moment. So the guideline says that no spurious tuple should be generated by doing natural join. So relation should be designed to satisfy lossless join condition. We'll discuss what lossless join is there. Lossless join is in the further questions. So spurious tuples occur when join keys are not primary key super key combination. We'll also look into this. So this was about the 4 informal guidelines. So you need to write all these 4 and explain it with a proper example. Now we'll look into normalization topic. So normalization is the process of organizing data in database. So we try to reduce the data redundancy. So normalization is necessary to remove. It is necessary to remove the redundancy, else it can cause anomalies. If anomalies occur, then it makes difficult for the database administrator to maintain it, and even for the users to execute the queries, it takes a longer duration or it becomes complex. So we'll start with 1NF. 1NF stands for first normal form. So it states that domain of an attribute must contain only single indivisible values, and the value of any attribute in tuple must be single value from domain of that attribute. So it disallows relation within relation, or relations as attribute values within relations. So only attribute values must be permitted, and they need to be atomic. 1NF means you should remember that it is atomic. So consider this example: product ID, color and price. So color, there are 3 attributes here, 2 and 1 values, 2 values, 3 values, 2 values in 1 value in the color. So this is 1NF redundancy, right? In order to reduce that, you will write 1R56, 1Y56, 1B56 separately. You'll form this table such a way that there are only atomic values in all the attributes. Once you have obtained this, the same values are being repeated, right? 56, 56, 56. In order to avoid this, what you can do is you can club product ID and color once, and then color and then price and product ID, such that 1, 2, 3 prices here and product IDs and colors. So here product ID, color and price have been reduced or decomposed to 2 relations R1, such that product ID and color relation to product ID and price. So this was the example for 1NF. To normalize the relation into 1NF, we need to remove nested relation into new relation and propagate primary key into it. So these are the primary keys here, product ID and product ID. The primary key of new relation will combine with the with the primary key of original relation. Yes, these 2 primary keys could be used. Moving on to the 2NF, looking into 2NF definition. So 2NF is based on the concept of full functional dependency. So before understanding 2NF, we need to look into the requirements. So a relation is said to be in 2NF if the database is in 1NF firstly, and all non-key attributes in the table must be functionally dependent on the primary key. That is the complete dependence, full dependence, fully functionally dependent. So every non-prime attribute should be fully functionally dependent on prime attribute. So if X determines A holds, then there should not be any proper subset Y of X for which Y determines A should also hold true. So in 2NF decomposition, if data is fully functionally dependent, only a part of primary key, then move that item or the data item and part of primary key to a new table. If other data item are functionally dependent on same part of key, then place them in separate table. So instead of reading this, we can explain this with an example. So this is the example. So here I have employee project. So SSN, primary P number, hours, ename, pname and P location. So here firstly, I can say that SSN ename is functionally dependent on SSN. So FD1 states that P number and Rs are functionally dependent on SSN. Okay. FD2 states that ename is functionally dependent on SSN, and then FD3 says that P location, P name are functionally dependent on P number. So here we can see that these are dependent on non-key attributes, right? In that case, we need to split that. So when you do 2NF, the one on which they are functionally dependent would be written in separate tables. So P number and Rs were dependent on SSN, so separate it, you'll get one table. Then ename was dependent on SSN, separate, you have written it in a separate table. P location, P name were dependent on a non-key attribute, which was P number is also a key attribute, sorry. So they have written it here again. So these are fully functionally dependent on the primary keys here. So this was about 2NF. Looking into 3NF, we have for 3NF there are two conditions again. So it has to be 2NF firstly and no transitive functional dependency. So all non-primary key attributes in a relation must be functionally dependent on candidate key. That is, no interdependencies among non-primary key attribute. So we'll understand what non-transitive functional dependency is. If x determines y and x determines z and x determines y and z is a subset of x, then x determines z and y determines z. So understanding this with an example, we have implied department here. So ename, SSN, bdate, dnumber, dname and dmanager are the attributes here. So dmanager is dependent on SSN. So is transitive functional dependency because dnumber is dependent on SSN and dnumber is dependent on dmanager SSN. Here dnumber is neither a primary key attribute nor a subset of employee department. So we encounter transitive functional dependency. To overcome this, we need to do 3NF normalization. So for that, we decompose it, set up relation that includes non-primary key attributes that are functionally dependent, that functionally determine other non-primary key attributes. So here, this was the condition, right? So on SSN, ename and department number and bdate were dependent, and on dnumber, dmanager and dname were dependent. Here, dnumber is not primary key nor primary key attribute. So that is that results to transitive functional dependency. So for that, we need to decompose it. So when we decompose, we write ename, SSN, bdate and dnumber in one table, and then dnumber, dname and dmanager in another table. Now if you check the second table, dnumber is the primary key here. So these two are dependent on the primary attributes. So there is no problem of 3NF here. Transitive functional dependency problem is avoided here. Next we have BCNF, that is stricter than 3NF. So it is Boyce called normal form. It is advanced version of 3.5NF. So the two conditions here are, it should be in 3NF form. For every functional dependency, x determines y, x should be a super key in the relation. So LHS part should be a super key always in BCNF condition. So looking at the example here, student ID is given, course is given, teacher is given. So student ID, course. So teacher depends on student ID and course. And teacher also depends on the course. But here, course is a primary key attribute. But then teacher is not a primary key attribute. It is not super key. In that condition, what we'll do, we'll split it up such that student, in student table, we have student ID and TID. Here we are making use of a third row. Okay, third attribute in order to connect these two. Okay, so when you club these two, you need to get the original, when you club these two, you need to get the original table back, right? So in order to avoid any loss of data or the information, you make use of TID here. So student ID and TID. Student ID, TID are the composite primary keys. TID is the foreign key which is connected here. Here TID is the super key because it is foreign key in the above table and primary key in this table. So teacher depends on TID and course also depends on TID. So this was about BCNF. I hope you have understood the normalization topic. I would suggest you to go through the written part here. You'll understand it better. So the last topic in fourth module we have is non-additive or lossless join property. So it ensures that no spurious tuples result after the application of project or join operations. These are algebraic operations, relational algebra topic. So I'll explain it in that particular module. So lossy design refers to a design that represents a loss of information. So such a design where the information is lost. So if a decomposition does not have lossless join property, we might get additional spurious tuples after the project and natural join operations are applied. So these additional tuples represent invalid info. Not only they represent invalid info, they also lead to the redundancy. The efficiency and the throughput would be reduced in this condition. So looking at the algorithm, we have, this is a complex algorithm, I would say. So input is universal relation R, a decomposition D such that the R is divided into R1, R2, R3, n parts. Okay. So a set of functional dependencies F. So we need to create an initial matrix with one row from Ri and one column from Rj for each attribute in Aj in R. Next, we need to set the values for all matrices. We need to find the matrices. Then we need to check this condition for each row representing, for each row I representing relational schema Ri, for each column J representing attribute Aj. If relation Ri includes Rj, then set S of I comma j as Aj. And fourth, we need to continue checking this loop till the result no longer changes. For each functional dependency x determines y in f, for all rows in S that have same symbol in column, that of x, make y columns also same. So fifth step is, if a row is made entirely of symbols, then decomposition has non-additive join property, else it does not. So here, let's consider the example. The relation R is given here. We'll decompose this relation in two parts such that R1 and R2. So we'll take XY and YZ as the combinations. If I write for XY, I'll get AB, BB and CC. For YZ, if I write BA, BB and CB. So, okay, I have from R1, I have decomposed it to R1 and R2. Now, if I have to join R1 and R2, I should make use of Y, because Y is the common one, a common attribute here, right? So with the help of Y, I can join X, Y and Z again, and I'll get the same relation again. So here, whenever a query is raised, which requires values of X and values of Z, I make use of Y. Yeah. So let's consider an example. So find value of Z if value of X is A. So value of X is A means this one. Value of Z I need to find. If X is A, I should get A in the Z. Okay, so this is what they are asking. So here we'll write select R2 dot Z from R2, and I'll perform natural join here R1, where R1 dot X is equal to A. So this is the query for this. Now I need to perform join, right? I need to join these two. So what is join? Join is, can be simply explained as cross multiplication of the values here. So in order to join, I'll write, first I'll consider AB and multiply it with all these. So I'll get BA, BB and CB. Next I'll take BB and multiply it with all these, BA, BB and CB. Next I'll take CC and multiply it with BA, BB and CB. So I have multiplied. So this was join. Now here I've considered natural join. So natural join says that only if the y value is same, select or else reject the other values. So here y value is B, here also B, here also B, here also B. But here it's not the same, so reject this. Here BB, consider this. Here again BB, consider this. Here it's not same, reject this. CCB, reject this. CCBB, reject this. CC. So I've obtained few relations. Let me write it down here. So X, Y, Z, if I construct the R table here, I'll take this R1, this was R1, this was R2, I'll take this as R3. I'll write A, B and A I have obtained. A, B, B, B. Here I have B, B and A. I have B, B and B. And here I have C, C and B. So when the decomposed relations are joined, I need to obtain the real original relation back, right? So that's what happens when you join. But then if you check here, R3 is not equal to R, because here there were 1, 2, 3 values, 3 rows, but then here there are 5 rows. So there's some variation here, right? So we can say that spurious tuples have been identified here. So ABA was here, but then BBB was here and CCB was here. These two are the extra ones. So these are the spurious tuples that I have obtained. So in this condition, this is not valid, right? So there's error occurring here. So the solution to this is, whenever we are decomposing and formulating new relations, the common attribute should be a candidate key. So it should be a candidate key for either R1 or R2 or for both R1 and R2. So let's take the same relation. Now I'll try decomposing it with R1 as X and Y and R2 as X and Z. So if I write for XY and for XZ, let me write. For XY, if I write, I get AB, BB and CC. And for yz if I write, I get for xz if I write, I get AA, BB, and CB. So find value of z if value of x is a. Here x value was a, here also a. So I had to obtain AA. Now I'll check if I get obtain AA here. Value of x is a, value of z is a. I have obtained it properly. So whenever you obtain the same relation, whenever I combine this, I'll obtain the same relation back. So that's what the lossless join property says. So it should obey the following conditions. If I add R1 or R2, if I do the union of R1 and R2, I should get the R original back. So that's what we have done here, right? So when I combine these two, I'm getting the original one back. And then if I do intersection of these two, I should not get null. So if I intersect these two, AB and AA, so if I intersect XY and XZ, Y and Z will go, X would be remaining. So this is not null. Next, R1 should be a candidate key or R2 should be a candidate key, or both could be candidate keys. So this was about the non-additive or lossless join property. So I hope you have understood. I would suggest you to go through the notes, the PDF which I've provided. In that there are multiple questions. So they usually won't give in this format, either 1, 2, 3 or ABC. It'll be in like proper attributes like a roll number, SSN and all. So you need to consider each one as XY. Then it'll be easy to solve in this way. So I have considered it as AB and I've solved it further. So this was about fourth module. I have tried covering all the major topics. So I would say that go through the PDF once. There are other topics also, just glance them once, but then be thorough with these topics. And fourth module is pretty easy and scoring module because it has algorithms and these numeric and these problems. You can easily solve them. And do subscribe to my channel. I'll be uploading notes and answers of other modules also. So stay tuned. Thank you.